So our next speaker is Professor Dorit Aharonov from the Hebrew University, and she poses a provocative question: should quantum computing interest Yakir? So what's the answer?
Okay, hi everyone. Okay, so it's really a pleasure to be here, and as I said, I've been in this business. First of all, I was thinking of what should I talk, and I think it's a difficult enough question to be somewhat interesting, both for Yakir and maybe for other people, and also for me to think about. Should quantum computing interest Yakir? And I don't know the answer to that. But before I go into this attempt to answer this question, I want to say I've been in this business of quantum computation for 27 years. I went to a lot of conferences with physicists, and carrying this last name of Aharonov with me, I think I'm among the four speakers of today. I can safely say that I'm the one who was most approached with this question, the following question: excuse me, are you by any chance related to Yakir Aharonov? So I already recognize this coming question just by the face of the speaker approaches me. So yes, I'm Yakir's niece. Yakir is my uncle, and to testify for that, I actually dug up my family root project, from which every kid does in Israel at the age of 12. And this is the picture I found of Yakir. This is, it says, the brother of my father, who's also here, Yakir. And I think this is a picture of Yakir taken at the age when he was younger, when I was doing this project. But you can already see, curiosity and vision are there. Okay, so let's try to answer this question of should quantum computing interest Yakir? And why is this question so difficult? Well, because it combines two things. One is the thing that Yakir, he loves the most: quantum physics, superpositions, measurements, entanglement, etc. And the other, I dare say, is probably one of the things that Yakir likes the least: technology. And you bet. Thank you, Nili. And okay, so how do these things marry? Okay, so they basically, you can track back the fact that they sort of were combined to a famous talk given by Feynman, already 1981, called Simulating Physics with Computers. And Feynman noticed a very important fact, that quantum many-body systems seem to be extremely hard to simulate by classical computers. In fact, it takes exponentially long to simulate them, because quantum systems of even 500 spins, for example, the description of their state requires 2 times 2 to the 500 size to describe, which is more than the estimated number of particles in the universe. So even writing the state of a fairly small quantum system is impossible. So classical systems cannot simulate directly, as far as we know, quantum systems. And so Feynman asked, how can we turn this question or this problem on its head? Maybe we can actually use quantum systems as quantum devices so that they can simulate themselves, be their own problem, and maybe also solve other problems more efficiently, exponentially faster possibly. And so this leads to the question, could computers made of, based on logic that comes from those weird ideas of superpositions and entanglement and so on, could they be dramatically faster? And, okay, so why is this question interesting? So one possibility to try to say it's interesting is a financial prospect. If you look at what's going on in the world now, well, this is an exponentially exploding curve of amazing amount of money going into this, with estimations of $700 billion investments in 15 years or so, less than 15 years, never mind. But I think I can safely say that this would not be a good answer to why would quantum computing interest Yakir. So let's try a different route. Maybe slightly more interesting, truly interesting, is the technological implications of quantum computation. So, which is actually the reason why all these companies are trying to build quantum computers and so on and so forth. And there are lots of those. There are lots of potential technological implications. In fact, it promises a technological revolution because not only that, like Feynman predicted, quantum computing promises to provide exponentially fast simulations of physical systems, they can also solve various other problems, like algebraic problems and topology-related problems and other problems, other combinatorial problems, exponentially faster than ordinary computers. And also, I mean, every human being would be extremely excited about the fact that they potentially revolutionize chemistry. So they provide potential new solutions for various issues related to the pharmaceutical industry and possibly addressing issues related to the climate problem, providing low-carbon technologies, new low-carbon technologies. So this is, of course, extremely exciting from the point of view of applications, but I think it's still not a satisfying answer to my question. Right, Yakir?
Right.
Thank you. Okay, so I think the potentially somewhat satisfying, possibly satisfying direction we might be able to find it by looking into scientific insights that come from quantum computation into quantum physics. And this has been a very rich source of insights, this quantum computation business, on quantum physics in the past 30 years. So we've seen implications or new sort of ways to look at very deep notions in physics from the perspective of computation. And I'm talking about notions such as complexity, universality, robustness and stability, and even new ways to look at questions that touch upon fundamental of quantum mechanics, such as the quantum to classical transition and the nature of measurements. So I want to go a little bit into this, along these, into this rabbit hole to try to see why that is so, and I don't know, maybe you'll tell me at the end if what's the answer. Okay, so for that, sorry? 42, yeah, thank you, Moti. Yeah, I'll tell you what's the question first. Okay, so for that we'll have to take 5 minutes and go into the side of the equation that is less liked by Yakir, as at least what I said, I don't know, which is the computation side, and ask what is a computation. So, okay, how many of you recognize this building? Not enough. Okay, this is an amazingly beautiful building called the La Sagrada Familia in Barcelona, designed by Gaudi more than 100 years ago. And it's beautiful. It looks like a sand castle. And it's basically the reason it looks like a sandcastle is it consists of arcs put on top of each other, lots and lots of arcs. And Gaudi, in order to design this amazing construction, more than 100 years ago, with no computer at hand, classical or quantum, he had to do something. And so how do you solve all these equations? Instead of solving equations, what he did is he took ropes with length that are proportional to the length of the arcs that he wanted to put one on top of the other, and he tied them together at the places where they should have leaned on top of the other arcs. And so he had a construction of ropes, and then he took those ropes and tied them to the ceiling, and instantaneously, gravity just calculated the equilibrium state. And of course, this is upside down, so you can see in the basement of the La Sagrada Familia a huge mirror underlying this construction where you can actually see the correct solution. So this is an example of a computation. It's a very beautiful example, very clever one, but it's not a a computational model. It doesn't perform general computations. So you actually have to do some work in order to define a model of computation that is capable of performing computations, not just of the structure of a particular church that you want to design, but any computation that you want to come up with. And Turing was the first to do it in his seminal work from the early 30s, last century, leading to classical computers. And Deutsch followed up with his definitions of the elementary units of information in quantum computers. Those are quantum bits, qubits, and quantum gates, the elementary steps in the computation. And I'm not going to define those today, but I'm just going to say, once you have, the computation is built out of these elementary steps, and once you have this model of computation made of elementary steps, you can actually start asking, what is the complexity of the computation? How long would it take to perform a certain computation? Okay? So with this model of computation, what happened right after the definition of that was a cascade of events. Deutsch was the first to do that, to ask this question of whether actually one can save anything by using the rules of quantum mechanics inside a computer in order to save something. And he looked at the following very, very simple problem. You have a function that takes a bit, either 0 or 1, and outputs a bit, either 0 or 1. And this function either gives the same answer to both bits or different answers. And that's the only thing you need to determine is whether they are the same or different. Classically, if you ask this question, you would need to evaluate this function twice, f of 0, f of 1. Quantumly, it turns out that if you evaluate this function on a superposition of the inputs and you use interference between the outputs, you can actually know the answer without, that's it. You don't have to evaluate the function twice, you evaluate it once. So this is a very, very beautiful example of how one can, it's like a crack in reality. Instead of 2 operations, there is just 1. But this saving of 1 operation led to a sequence of events very quickly, in which Deutsch and Josa, Bernstein, Vazirani, then Simon, and then Shor, led to an exponential improvement in the number of operations. Actually with the same idea of Deutsch, but just sort of noticing that it can be enhanced more and more and applied in different contexts. Okay, so this was very exciting in '94. This is Shor's algorithm that actually shows that, doesn't prove, David, but indicates, and many people believe, that quantum computation can provide exponentially faster solutions to very, very difficult problems, such as factorizing integers, which is a problem notoriously hard for centuries. Okay? So, following that, there were several algorithms that came out, and like simulating physics, topology related, like those that I mentioned before. Okay, enough with computation. And back to physics. So what does it tell us about physics? The fact that we see that, so of course we don't yet have quantum computers, but if we would implement full-fledged quantum computers, we would be able to solve problems exponentially faster than ordinary classical computers. What does it tell us about physics? Well, the first thing that if you have to dig a little bit into that, but the first thing that maybe the most important thing is that in fact, quantum computation or full-fledged quantum evolution it actually corresponds to a new state of matter. It's a state of matter where, in fact, these are sort of potential realizations of quantum computation. All those systems are potentially truly quantum. Truly quantum, I mean not just capable of exhibiting superposition between two states or entanglement between 2 particles, but actually having a microscopic system in which all of its degrees of freedom can be sort of manipulated to control and to evolve the entanglement and the coherence in it in a way which is completely quantum and is completely not classical. Meaning capable of processing information in a fully quantum way. We call it quantum universal. And in fact, all those systems are equivalent in that sense, even though they're extremely different systems. Not going into the details of those, but they're different physically. They're very, very similar in the fact in how they process quantum information. It's extremely complex. And this corresponds to some kind of a phase transition, or at least resembles a phase transition, like between ice and water, where this regime, this quantum universal, highly complex regime corresponds to this ice, and globally classical corresponds to water. We don't understand this transition. We don't understand this phase of matter. We haven't seen it yet. I mean, we predict that it exists, but we haven't seen it yet. And I should stress that this is very different than the very impressive and beautiful results showing, for example, entanglement between macroscopic classical objects, but only simple entanglement between macroscopic classical objects. This is entangling drumheads, which are macroscopic in size, but still, it's not what I mean by completely quantum. What I mean is a phase or a state of matter where actually you can process information of exponentially many degrees of freedom. Okay. Okay. So this is a very interesting prediction of quantum mechanics, of many-body quantum mechanics. It's basically extrapolating the rules, the laws of quantum mechanics to many-body physical systems. Okay. So first of all, maybe the first question is: so far, the definition of this new state comes from computer scientists. This is not a good situation. We do want physicists to take over this question and understand this new state from using physical language. Okay, so that's the first question. The other question, which comes together with that, or which is implied by that, is, I think, a very interesting question, which is, what is a physical experiment? So let me, I don't know how long do I have. Do I have 3 more minutes? I think yes. Okay. So 4. Thank you. So what is a physical experiment? Okay. So on the side, on the left side, you see the theoreticians. You might have known that this is the side of the theoreticians, and on the right side you see the experimentalists. And a physical experiment, say, to test the physical theory, the Newtonian mechanics, would be to have those calculate some predictions, and to have those try those predictions and compare. So I would call this the predict and compare paradigm. Okay, if you've listened to what I said and also believed it, you would have noticed that one side of this picture is impossible if what you're trying to study and to test is many-body quantum mechanics. Which one? Left or right? Okay, this is touchy now after the elections. Okay, so actually it's the left side that is impossible. And the reason why it's impossible is because basically we cannot predict. The whole point of quantum computation is that it does something that on many-body quantum systems, it does something that we cannot predict by classical systems efficiently. Otherwise, it wouldn't have been interesting to come up with a quantum computer. It's exactly because it's hard to simulate. So we cannot make the predictions in order to test the theory. Not of those, exactly those phenomena that are interesting because they are so difficult to predict. So can we test quantum physics in this regime? inherently not in the predict and compare paradigm. So how can we test it? Turns out that, that it is possible to test it using ideas from computer science. This is sort of us, little ones, against something which is completely not understood, this beast there. How can we test it? How can we verify that really what's going on is really quantum mechanics as we understand it? Well, we add interaction and randomness. And let me try to give an example or some kind of a story that maybe provides a way to understand this. Okay, so in 2 minutes, it's a short story. Okay, I'm a magician, and I know how to count the number of leaves in a tree in the blink of an eye. And there are no windows here, but if there was a window, you could have tested me by pointing out to some tree, and I would have told you, this tree has 9 million leaves. How do you test it? Well, one way is to count the number of leaves. That would take you a long, long time. But the other way is to ask me to turn around and then pick randomly some small number of leaves, turn them away from the tree, and then ask me to count again. If I'm consistent with that number that you tore, and if you tore 3, I tell you 9 million minus 3, well, maybe I was lucky. You do that 10 times. If I'm lucky in all of them, you're convinced. Even though you don't know how to count the number of leaves in the tree in the blink of an eye yourself. And this is a difference, and this has been actually raised in several talks earlier, both in Sandu's and in Michael's, that there's a big difference here between knowing something and being convinced of it and understanding it. And maybe that also connects to Ranit's talk later on. Okay, so just to wrap up, this idea basically was actually used to design, not exactly this idea, but based on this idea of interaction and randomness, you can actually design an experiment which is interactive to test quantum mechanics, even when we cannot predict it, even in this high complexity regime. So this leads to a new type of experiment, which is adaptive, interactive. It's a new way to think of experiments. And nowadays, there are lots of results showing that if you think of experiments in using structured interaction, you can actually achieve exponential saving in resources. So you can think of quantum measurements and quantum experiments in a way which involves sophisticated interactions between what you're trying to measure and the measuring device. And you can think of the measuring device as involving some kind of quantum computing ingredients in it, and that could save you exponentially many resources in certain situations, but it also opens up the possibility of completely new experiments where things are much more structured between and much more sophisticated on the device level. So let me end here by just saying, okay. So by just saying, first of all, happy birthday, Yakir. And I don't know if I've convinced you that quantum computing is interesting, or why it should interest you. But I want to say that I want to thank you for at least inspiring me to really. I think you've inspired me in our conversations, many conversations when I was. Also younger and in various occasions, to try to see what is it, how can I actually think of what it really means for something to be interesting. So thanks.